All right, welcome everyone. Today we have a speaker from MIT, Dr. Luqiao Liu. Luqiao is an associate professor of electrical engineering at MIT. He received his bachelor degree from Peking University in 2006 and a PhD in applied physics from Cornell in 2012. He then worked as a research staff member at MIT Watson Research Center. I guess that's in New York Heights, right? Before joining the MIT faculty in 2015, Luqiao's current research focuses on spintronic materials and devices for memory, logic, and communication applications. Luqiao has picked up multiple awards, prestigious awards, I'd say, including William Macmillan Awards, NSF Career Awards, Air Force Young Investigator Awards, and International Union of Pure and Applied Physics Young Scientist Awards. Today, he's going to tell us about his studies on both ferromagnetic magnons and antiferromagnetic magnons in different systems. So without further ado, Luqiao, please take it over.
Thanks, Julie. Yeah, so first of all, I would like to thank you for giving me the opportunity of talking about our recent work. So it's a great honor to have this talk today. So today I'm mostly going to talk about the spin wave excitation in magnetic materials. So I will talk about two different materials. One is antiferromagnet. How do I change my, okay. One is ferromagnetic material and the other is antiferromagnetic material. So I will show how we can possibly control the transport of spin wave or magnons in those two magnetically ordered materials. So first of all, I think all of us have learned a little bit about spin waves or magnons in our solid state physics. So we know just like other waves like photons or phonons, the magnons or the spin wave is also another form of waves inside solid state materials. So just like elastic waves or phonons, spin wave or magnons also can have very short wavelengths. Basically, the bottom limit for the spin wave wavelengths is just the lattice constant in angstrom order magnitude. And also compared with other forms of waves like light, spin wave could potentially have stronger interactions with charge. We know inside solid state materials, there is strong spin orbit coupling. So that means potentially you can utilize electrical approach to control the excitation of spin waves more efficiently compared with photons. And also for magnons, it usually covers a wide frequency range from a few gigahertz, which is usually used for telecommunication, up to terahertz, so which can be useful for terahertz detection, terahertz spectroscopy. So that's another unique advantage associated with spin wave. And finally, one significant difference between spin wave and elastic wave or light wave is that actually you can have some stationary magnons. So that means they can have zero velocity, zero wave vector, but at the same time it can have finite frequency. Of course, here I showed the dispersion relationship which starts from zero, but it's not necessarily the case. So by applying an external field, you can open up a gap so that you can have finite energy magnons, which even have zero velocity. I think this is different from photons, the light wave case. Okay, so this is about some basic properties about magnons, and also some of those unique properties associated with spin waves can be particularly useful for applications. So here I would like just to name two of them. First of all, spin waves have some built-in nonlinearity. So I think these days people talk about quantum information processing, quantum computing. Actually, to a large extent, my understanding is that quantum computing is to utilize nonlinearity of a certain quantum system. For example, the ideal system for doing quantum computing is a two-level system. So there are only two levels. So that's basically highly nonlinear. So for spin wave, although it's not a very good nonlinear system in the sense that it has more than two energy levels, but still there is nonlinearity. The way to understand it is that you can imagine a magnetic material as a macro spin, so basically a big spin. So there will be multiple energy states. So basically you can excite this the quantum number of the spin angular momentum along the z direction from all the way from minus n to the positive n. So as you can see from this figure, actually the spacing between neighboring energy levels are equal. In this sense, it's similar to the harmonic oscillator or similar to phonons or photons. But on the other hand, there are only limited number of available states. So there are only 2n or 2n plus 1 total number of states. So that means there is a fundamental nonlinearity there. So after you reach the highest SZ number, you cannot further increase the magnetic quantum number. Similarly, if you are in a minus n state, you can also not further lower it down. So that's the reason why we see for spin waves, there is this kind of nonlinearity. For example, if you look at this operator's definition, it has this nonlinearity term. So that's the reason why usually people find it useful to use it as a frequency up or down converter. For example, you can convert information from the gigahertz domain up to the optical domain or backward. So that's one possible way to utilize the nonlinearity inside spin wave. There is another property I think that will be highly useful for these days information processing, that is non-reciprocity. Usually when we say non-reciprocity, we mean the signal can go from one side to the other side, but not propagate backward. This is useful because, for example, in quantum computing, you need to avoid the back action induced noise introduction into the system. So that's the reason people utilize this kind of magnetic material to realize non-reciprocal components, just like a microwave circulator or maybe an optical isolator. So actually for spin wave, in certain specific structures or with some mechanisms, actually you can realize asymmetric dispersion relationship or asymmetric damping. So that's how you can realize those non-reciprocal components. Okay, so because of those unique properties, actually since a long time ago, people start to propose to utilize spin wave to realize some functions of information processing or some functions of computing. For example, this is called wave-based computing. People try to propose utilize light to realize this kind of wave-based computing, and spin wave just can potentially act as a similar role. So there is a very nice review paper in this journal, which talks about how to excite, detect, and also utilize magnons to process the data. So a typical device structure that can be utilized for realize this kind of wave-based computing is something like this. So you can imagine you have one spin wave signal coming in, and then you can split it into two branches. And when the spin wave propagates in those two branches, you utilize two individual gates to control the propagation of the waves in those two channels. And finally, if you combine those two waves, you will get some interference pattern. So depending on whether you get a constructive or destructive interference, you can get 0 or 1 output. So this is one typical geometry that people propose to utilize spin wave to realize wave-based computing. As you can see here, one of the key components to realize this idea is to realize this kind of gate control. So if you can have a way to electrically control the spin wave propagation, then you are closer to realize this kind of device structure. Okay, so now the question is, how can we modulate the transmission of spin wave or magnons? So is there a spin wave modulator available from the market? Well, before we talk about spin wave, we can also first look at light wave, because that's probably the most mature technology available to us these days. We'll talk about photons or light wave. We know there are various types of optical modulators that you can buy from market. So usually they are quite big. The reason is there is usually weak light matter interaction or electrical optical interaction. So you need a quite large volume in order to realize efficient control over the light transmission. So actually these days people are trying to integrate the light modulator, the photonic modulator on some integrated circuit. That's some ongoing research. I think there are some very exciting results here. Okay, now let's look at spin wave. Let's ask, can we also realize similar magnon modulators? So I think in principle, there can be some advantage. In the sense, first of all, spin wave, as I said earlier, can have very short wavelengths, below micrometer or below nanometer. So in principle, you can probably realize it can have very small footprint. And secondly, there are some mechanisms which can provide strong spin charge interaction, so that possibly you can modulate magnons much more efficiently. Okay, so that's basically some principles. So today I'm going to talk about two experiments where we try to control the propagation of spin waves inside magnetically ordered materials. In the first one, we utilize the magnetic domain structure inside a ferromagnet to control the spin wave or magnon propagation. And in the second case, we try to manipulate the neo vector inside the antiferromagnet to control the spin transport. Okay, so as I said, how do we control the spin wave propagation inside the magnetic ordered system? So what are the existing methods? So actually, if you look at state of art, one thing that you can utilize to control the spin wave propagation is the so-called magnonic crystal. I think this is just a concept that people borrowed from the photonic crystal field. You know, when you have a crystal, if you pattern it into some periodic structures, then you can basically engineer the band of these those photons or magnons. And then for certain wavelengths or certain frequency, actually the propagation of photons or magnons are forbidden. And then you will find some form some band gap for magnons. So this is basically the magnonic crystal concept. And use this, you can control the propagation of certain spin waves. And there is also another method, which is try to utilize some local magnetic field to modulate the propagation properties of spin wave. So the idea is quite simple. So you can imagine if you have a conducting wire, and if you apply some current through this conductive wire, then that will generate some Ørsted field due to the Ampere's law. And those Ørsted fields will change the local magnetic field distribution around this region. So now you can imagine if you have some spin wave propagation that goes under this conductive wire, then they will experience a different field. And then that can change the property of this transmitted spin wave. And more recently, actually, people start to talk about utilizing the current-induced spin torque, so the spin transfer torque concept, to control the damping of a magnetic material. So by applying this kind of spin torque, you can increase or decrease the damping. So that can be used to amplify or suppress the propagation of spin waves. So if we summarize those existing techniques, we will find that usually they require quite large control terminals. So you need quite a large footprint in order to realize those structures. And another downside is that usually those control are volatile. So for example, if you utilize electric field or electric current to control the spin wave propagation, you need to keep the current on. As soon as you withdraw the current, then this control terminal disappear. And finally, in most of those existing demonstrations, people show that you can control the magnitude of spin wave propagation. What about phase? And we know the central component of phase of wave-based computing or wave-based information processing is to adjust its phase. But so far, I don't think people have shown that we can modulate the phase of magnons or spin waves very efficiently. So that's the reason we turn to a different structure that is basically a domain wall structure, try to utilize a magnetic domain wall to modulate the spin wave transmission. So first of all, let me introduce the concept of magnetic domain wall. So magnetic domain wall is just like a green boundary in the sense that you can, on a piece of magnetic material, you can have multiple domains. So for example, in this case, the left side, the equilibrium spin orientation is pointing up, and the right side, the equilibrium spin orientation is pointing down. So between the up and down domains, there can be a boundary, and this boundary is called magnetic domain wall. Okay, so as you can tell, this magnetic domain wall is given free. So you can always get some domain boundaries inside your magnetic material. So you do not need extra patterning or extra lithography to define these structures. Actually, theoretically, people start to consider this kind of geometry long time ago, where people try to say, hey, if we apply a spin wave, excite spin wave on the left side of this domain wall, and then let the spin wave propagate through this domain wall. And then on the right side, if I detect it's the transmitted spin wave, what would I expect to see? So actually, people utilize theoretical method or numerical method to visit this topic. And for example, people show that you do observe some phase delay after the spin wave goes through this boundary. And sometimes you can also get a very large reduction of the spin wave magnitude. So depending on the details of this boundary. But experimentally, it hasn't been demonstrated until our experiment. The reason is this structure actually is not very easy to realize. Particularly, it's not very easy to realize a very simple domain. For example, you only have two domains. On the left, you have up. On the right, you have down. Usually, you get multiple domains in a magnetic structure, but usually those are quite random. You get many, many different domains, or you get no domains. So it's not that easy to control this kind of magnetic property. So basically, this comes our experiment. So the way that we do this experiment is that we utilize this kind of technique known as spin wave spectroscopy. In this spin wave spectroscopy, we excite and detect spin wave using some microwave antenna. So on the left side is a transmitting antenna where we have applied a microwave signal. And those current in the microwave frequency will have a Earth-side field due to the Ampere's law. And those Earth-side fields will inductively excite the spin wave oscillation in the underlying ferromagnetic field. And then those propagation of the magnetic oscillation, which is, by the way, the spin wave, can be detected by the second antenna located on the right side. And this second antenna is the receiver antenna. Because of the oscillating magnetic moment will cause oscillating flux, magnetic flux through those effective loops. And then that will give rise to electric motion force. And that can give rise to a microwave signal, which you can detect using a vector network analyzer, for example. So here, the ferromagnetic film is a spin wave channel. For this experiment, actually, we utilize a Cobra-nickel multilayer as the underlying spin wave channel. The reason that we choose this kind of multilayer structure is because it has some unique magnetic properties. So I will explain in the next slide. So basically, this is an optical microscope image, which shows the spin wave channel. And then for this pink region, actually, that's the silicon oxide spacer. So you want to electrically isolate the antenna and then the bottom spin wave channel, which is conductive. And then finally, you have the micro antenna, which made in a sub-micrometer range. Okay, so this is a structure. And then let me see a little bit about this Cobra-nickel multilayer structure. This Cobra-nickel multilayer structure is unique in the sense that it has some perpendicular anisotropy. So basically, because of the interfacial properties between cobalt and nickel, actually the magnetic moment in its equilibrium tends to align autoplane. So they try to stand up or stand down in this multilayer structure. And this anisotropy is actually tunable by changing the thickness. And as you can tell from this magnetization loop, where we apply the field in the autoplane direction. So it has a perpendicular anisotropy. So in the equilibrium state, in the under zero field, the moment is either pointing up or pointing down. And also it has, you can make it quite thick by repeating this kind of stacks. You can make it fairly thick, maybe few 10 centimeters. So that means it can have enough volume to carry the spin wave. So there are some other thin film magnet which has perpendicular anisotropy, but usually those are very thin. But in this case, we want a thicker, larger volume, a thicker cross section. And finally, this perpendicular anisotropy material, this Cobra nickel multilayer, has a decent magnetic damping. Since we are talking about spin wave, the damping is just the inverse of the quality factor. So if you have a very high damping, you can imagine the spin wave will propagate, will decay very quickly. So you will not be able to detect much signal. So we want as low damping as possible. So this one does not have a very too impressive damping, but still this 2% of damping coefficient is enough for us to observe some signal. Okay, so basically utilizing this Cobra nickel multilayer structure and then utilize these antenna pairs, we are able to detect the transmitted signal. So this figure shows a typical transmission signal detected from a network analyzer as represented by S21, which means the transmitted signal from port 2 over the input power at the channel at port 1. So as you can see, we have both the real part and the imaginary part because the transmission coefficient by itself is a complex quantity. Okay, so it looks like we are able to detect some magnetic oscillation or spin wave oscillation signal. You can see that as a rarest frequency, there is a dip or there is a peak in the real part or the imaginary part. But how do we know that it comes from real spin wave transmission instead of just a direct coupling? You know, if you have two antennas, even if you just leave it in air, there will be some direct coupling, crosstalk. How do we know that's not the case? Well, we can do a control experiment where we cut this spin wave channel using, for example, some argon RML. Then you can imagine the spin wave will no longer be able to propagate through. But now if we detect the transmitted signal using the same vector network analyzer, and the signal disappears. So actually this control experiment suggests that what we detect does rely on the spin wave propagation instead of just a simple crosstalk. Okay, so this is a spin wave detection just in a uniformly magnetized ferromagnetic film. Next, we would like to introduce domain wall. So the first question that we need to address is that how do we see the domain wall? How do we form a domain wall and how do we locate its position? Particularly, how can we put a domain wall exactly between those two antennas? Well, here, in order to visualize domain wall, we utilize a MOC microscope, which is a magnetic optical Kerr effect microscope. The Kerr effect is just similar to a Faraday effect. So as you know, Faraday effect is basically you can induce some phase change depending on whether it's left circular polarized light or right circular polarized light when the light gets transmitted through a magnetic crystal. So here, Kerr effect is very similar, but usually it works in a reflected configuration instead of the transmission configuration. So utilizing this MOC microscope, we are able to identify different magnetic domains. So this top figure actually shows a spin wave channel where all of the domains are uniformly magnetized. So the magnetic contrast is represented by this bright yellow color. As you can tell, here is bright yellow, bright yellow, bright yellow. And there are some two regions which are the light reflection from antenna. So basically those block the magnetic contrast. But at least from those three regions, we can tell that they have uniformly magnetized orientation. And in the bottom, actually, this represents the case where you can form a domain wall. So as you can see, between the two antenna, in the middle, there is a boundary between bright yellow and then this dark blue. So actually this reflects the magnetic domain, the magnetic domain wall. So now we can measure the transmitted spin wave in those two cases. So for the first case, which is uniformly magnetized, we get this transmitted signal. And then for the bottom case, where there is a one domain wall, we get the other transmitted signal. If you compare those two transmission spectrum, you will notice that actually they look different. The first difference is that if you look at the y-axis scale, the uniformly magnetized spin wave channel have much larger magnitude compared with the domain wall case. So it's about 10 dB reduction for the case with the domain wall. Besides this magnitude difference, you will also notice that the phase is different. For example, here, for the real part, under resonance, you get a dip for the uniformly magnetized film. But for the film with the domain wall, you will notice that this is a peak. So basically, this indicates a 180 degrees phase shift. Of course, we can repeat this kind of experiment under different configurations, which I will skip here. But here, I would like to say that we can reproduce this kind of spin wave transmission property by doing some micromagnetic simulation. So here, OOMF, OOMMF, is a package people utilize to do multi-domain micromagnetic simulation. So from this kind of simulation package, we can find that when there is no domain wall, which is the top case, we get one transmission pattern, and when there is domain wall, which is the bottom case, there is another transmission pattern. By the way, the color here represents the peak or valley of the spin wave transmission. And by comparing those two, you can tell that there is a phase inverse after the domain wall. And also for the domain wall case, the transmitted spin wave is also much dimmer, much darker. Intensity is much lower compared with uniform case. So basically, this is to verify that this is to reproduce what we saw in our experiment. The more detailed study shows that this phase change from the domain wall across the domain wall comes from the dipolar interaction. So it comes from the magnetic long-range dipolar interaction. And it's robust against frequency change or sample dimension variation. Okay, so this is basically to show that we can utilize this kind of domain structure to modulate the spin wave transmission. So now actually we can make a comparison with the electronic version. So actually for the electronic version of this kind of magnetic domain controlled electron transmission, it's already well known. You might have heard this term of giant magnetoresistance. Giant magnetoresistance is the case when you have two magnetic domains. If those two magnetic domains are anti-parallel aligned, you get a low transmission rate or high resistance states. And when those two are parallel aligned, you get a high transmission state or low resistance. So our demonstrated effect where the magnons get attenuated by this domain wall is just similar to what people showed earlier about those kind of giant magnetoresistance effect. But of course, the extra feature we observe here is that there is also a phase change. But for electrons, there is no phase because it's not a wave. Well, at least we are considering the classical part of electrons. And then for the electronic version, we also know there is a reciprocal effect of this giant magnetoresistance. That is known as spin torque or spin transfer torque. So what happens is that if you apply a large enough current, this large enough current which carries spin will flip one of the domain from parallel to anti-parallel location or from anti-parallel to parallel location. So this is known as spin torque. So correspondingly, it's natural to ask, can we possibly realize the same thing by utilizing magnons? For example, can we utilize a magnon current or spin wave current to flip the orientation of magnetic domains? So that's what we try to look into in the following. So we try to show that there is a magnonic spin current induced domain wall motion. Well, again, this concept has been studied a long time ago, theoretically, because this structure is not too hard to visit in theory. So you can imagine you have spin wave transmitting across the domain wall, and then for the upstream, left to the domain wall, the magnons actually they carry spin down angular momentum. And then when the spin wave goes to the right side, transmitted to the right side, actually those magnons carries spin up angular momentum. So actually the reason is the equilibrium position for those magnetic domains switched. And more specifically, this spin current on the left or right side can be represented by this formula. So here theta is an oscillation angle, it's a precession angle, and Vg is group velocity. So this gives you the spin current on the left or on the right side. Now you can imagine this domain wall boundary region corresponds to a sink or a source for spin current, because up spin comes in, down spin comes in, up spin comes out. So that means this is a spin sink. So we know due to the conservation of angular momentum, whenever there is a divergence of spin current, or whenever there is a spin sink, then there will be a spin torque effect due to the conservation of angular momentum. And if this spin torque is high enough, it can cause magnetic switching. So we try to verify this experimentally. The way that we do it is still we have this spin wave channel on the bottom, and then on the top we place one microwave antenna to excite the spin wave. But before we apply these spin wave powers, we nucleate the domain wall, and they let the domain wall to sit left to this antenna. For example, this yellow green boundary is a domain wall. After we apply these powers, we found that actually the domain wall moves closer to the antenna, so it moves against the spin wave propagation direction. And this behavior actually is the same no matter we have a up-down domain, means the left side is up, right side is down, or down-up domain, where the left side is down, right side is up. So in both of those two cases, the domain wall, the domain boundary always move against the spin wave propagation direction. So basically stops somewhere below this antenna. Okay, so actually this is consistent with the previous theory, where you do expect the domain wall moves against the spin wave traveling direction. But how do we know that this does not come from some trivial effect, like a thermal effect? For example, if you apply some microwave powers, it can heat up the local region, and then maybe induce some deepening of the domain wall. So how do we know that's not the case? Well, what we can do is that we can compare the domain wall deepening when there is a spin wave excitation versus there is no spin wave excitation. By no spin wave excitation, what I mean is that we apply a microwave source, microwave current, but this microwave current is at a frequency that is far away from the rareness condition. And we found that only under the rareness condition we can induce this kind of domain wall deepening. But for the off-rareness case, there is only simple trivial thermal effect. Actually, from this kind of switching phase diagram, we can identify that the switching mechanism is a spin transfer or spin torque effect rather than thermal contribution. So I will skip the details about this. Okay, so far, what I showed is that in a ferromagnetic material, by utilizing the magnetic domain structure, we can modulate the transmission of spin wave. Particularly, we can change its phase by about 180 degrees. And moreover, we show that we can utilize a large enough spin wave to push or to move the domain wall position to induce magnetic switching. So that's the first part of my talk, which is on ferromagnetic material. And in the following, I would like to switch to a different magnetic system, which is still magnetically ordered, but this time it's antiferromagnet. I will talk about how we can possibly utilize the new vector orientation to control the spin transport inside antiferromagnet. So first of all, let me give some brief introduction about antiferromagnet. We know for magnetic ordered materials, solid materials, there are two main categories. One is ferromagnet, and the other is antiferromagnet. So antiferromagnet, to a large extent, might be more common in real world compared with ferromagnet. The reason is we know when you talk about super exchange, meaning when two magnetic atoms are basically have the exchange interactions through a intermediate oxygen atom, then their exchange interaction is usually prefers anti-parallel orientation. As we know, there are many different types of oxide compound. So that's the reason I say antiferromagnet might be overwhelmingly more popular in real world compared with ferromagnet. But of course, for technological application, antiferromagnet might be less important at this moment. The reason is because the two sublattices cancel with each other, they have opposite alignment. So there is not a net magnetic moment. And then you cannot use an external probe to probe its state. Also, you cannot control its state. So that's the reason why antiferromagnet, to a large extent, hasn't been explored in electronic world. But because of those cancelled magnetic moments, that could be some advantage, particularly because of the absence of this net moment, that street field. Then you can have potentially better robustness against external perturbation. So imagine if you apply an external field onto this kind of antiferromagnet, it does not really care. And also, there is another important feature that people notice these days, that is, there can be a very high intrinsic frequency associated with antiferromagnet. Because of the exchange interaction between the two sublattices, that effective exchange field is usually on the order of thousands of Tesla, which is a number that you can never realize with real experimental environment. So correspondingly, the oscillation frequency or the spin wave frequency can be in the order of terahertz, so which is much higher than ferromagnet, which can be useful. But now the question is, what about what's special with the spin wave inside antiferromagnet? So let me explain a little bit about the spin wave excitation inside antiferromagnet. So first of all, depending on the magnetic anisotropy of antiferromagnets, there are two categories. One category is known as this kind of easy axis antiferromagnet. By this name, you can imagine that the equilibrium position for the spins in this easy axis antiferromagnet is this single axis. It's either pointing up or pointing down. So that's the easy axis. That's the equilibrium orientation. In those kind of easy axis antiferromagnet, the magnon excitation or the spin wave eigenmode are those two. So basically, one is left circular polarized, and the other is right circular polarized. And each of them carries finite spin angular momentum. One is down, the other is up. So basically, this is the eigenmode inside easy axis antiferromagnet. And correspondingly, there is another category of antiferromagnet, which is known as easy plane antiferromagnet. For easy plane antiferromagnet, their equilibrium position for spins are in a certain plane. So any orientation within this plane can be an equilibrium position. So for example, in this case, for layer 1, it points to the left, and for layer 2, it points to the right, and that alternate with each other. So under this kind of magnetic property, the eigenmode for magnons is actually those two. Usually we call them linearly polarized magnon mode, or actually it's a highly elliptically polarized magnon mode. One is within the long axis, for one is within this easy plane, and the other is perpendicular to this easy plane. One thing that we know about those two eigenmodes is that although they are elliptically polarized, but those two precession perfectly cancel with each other. So the two sublattices oscillation perfectly cancel with each other. So the angular momentum carried by those two magnon modes are strictly zero. So there is no angular momentum. This is in contrast with the easy axis case. In easy axis case, either of those two modes can carry finite angular momentum. Okay, now the question is, can we possibly utilize the eigenmode inside the antiferromagnet to transfer spin, to use it to carry spin current or transfer spin angular momentum? Is that possible? First, again, let's look at easy axis first. Easy axis antiferromagnet. As I said, for easy axis antiferromagnet, we have those two eigenmode. One is left circular polarized, the other is right circular polarized. Each of them can carry finite angular momentum. In order to excite one of them, what you can do is that you can utilize non-equilibrium spins. For example, if there is a way to generate some excessive spins, electron spins, and inject those excessive electron spins. And those injected spins can transfer their angular momentum onto one of those two magnon mode. And then the magnon can further carry the angular momentum and propagate. Well, the exact way that one can utilize non-equilibrium spin, one can generate non-equilibrium spin and excite one of the magnon mode is through this so-called spin Hall effect. So if you are not very familiar with this concept, you can look at this schematic. So the spin Hall effect is where you apply a charge current longitudinally. And then you will notice that spins along different directions will get deflected toward different sides. And finally, they will accumulate onto different surfaces. By utilizing this effect, you can get spin accumulation. And spin Hall effect is an intrinsic property of some materials. For example, it's usually most significant inside heavy metals like platinum, tantalum, tungsten, etc. So actually utilizing this structure, utilizing this effect, people demonstrated this kind of non-equilibrium spins induced magnon excitation inside the antiferromagnet. Actually, this work was published 2 years ago by the Klawi group from Germany, where they utilize a platinum wire. By applying current inside the platinum wire, they can generate excessive spins. And by utilizing those excessive spins, they transfer the spin angular momentum onto one of the magnon mode, and one of these magnon mode will actually propagate to the right side of this magnetic insulator. By the way, this is a magnetic insulator. And then on the right side, they utilize a platinum to detect this transferred spin angular momentum through the inverse spin Hall effect. So by the way, inverse spin Hall effect is just a reciprocal effect of the spin Hall effect, when you have excessive spins that can generate a longitudinal current. So this type of device geometry, you can understand it as a non-local charge transfer that is mediated by some spin excitation. So here, a magnon excitation inside the easy axis antiferromagnetic insulator. Okay, so this is about easy axis antiferromagnet, which is straightforward because, as we said, there are two eigenmodes that carries spin angular momentum. The next question is it possible to transfer spin angular momentum, do the same thing with an easy plane antiferromagnet? So just now I mentioned the biggest difference between easy plane and easy axis antiferromagnet is that easy plane antiferromagnets, the two eigenmode, neither of them carries angular momentum. So now if you also inject non-equilibrium spins into the antiferromagnetic insulator, can it still carry angular momentum? Can it still mediate the charge transfer as shown in the previous experiment? So that was a question that we tried to answer with this experiment. So first of all, let me talk about the materials that we utilize. So here we utilize an easy plane alpha iron oxide thin film. Alpha iron oxide is a hexagonal structure. It's antiferromagnet. As you can see, that this is a C plane, and then the spins in the easy plane phase actually oriented within this C plane. It has a decent lattice match with a sapphire substrate, alpha aluminum oxide. You can tell from the XRD data, there is very narrow peak. And from AFM scan, you can also see that there is this kind of triangle shape, which indicates epitaxial growth. So, well, one unique feature associated with alpha iron oxide is that it has a finite magnetic moment. Although it's an antiferromagnet, but it has very weak ferromagnetism. The reason is those two sublattices are not exactly antiparallel with each other, but instead they form a small angle. This canting is caused by this antisymmetric exchange, or known as Januszewski-Moria interaction. So this prefers, instead of antiparallel alignment, it prefers a perpendicular alignment. But in this case, it gives you a finite angle. This angle is about 0.1 degrees. It's very small, which gives you a very tiny net magnetic moment. So this residual moment is about 1/1000th of regular ferromagnet, like cobalt or iron. But that's enough for you to use it as a handle to use external field to reorient its orientation. So for example, here we can utilize a field that is below 1 Tesla in order to reorient this new vector direction. Okay, so that's the reason why we utilize this special antiferromagnet. Again, here we try to repeat the experiment that I explained earlier. So the magnon-mediated non-local charge transfer. So on the left side, we have a platinum spin Hall channel where we can generate excessive spins. And on the right side, we convert those transmitted spin signal back into some charge current or charge voltage. And then the alpha iron oxide is located in between. We utilize the external field. By rotating this external field within this film plane, we can reorient the new vector direction. So by measuring the non-local voltage that we detected on the second platinum bar, we do observe some non-local voltage as shown on the right side of this figure. So this suggests that, okay, there is a non-local charge transfer, but how do we know that it is magnetic? How do we know that it is caused by the mediation of the spin excitations instead of some leakage? For example, there can always be some leakage between two electric wires. How do we know that's not the case? Well, the reason that we can tell is because it has this kind of magnetic field dependence. So this angle theta is basically the applied field angle. So when we change this in-plane field angle, and we can change the new vector orientation, we found that actually this non-local voltage actually also has this kind of oscillatory behavior, which is consistent with what you would expect from a magnetic system. So basically this indicates that the magnetism or magnetic excitation inside this alpha iron oxide does get involved in this experiment. Moreover, we can also study this kind of charge transfer as a function of the spacing between the injector and detector location. And you can see that this transmitted signal actually reduces as the spacing increases. And it can survive under a 1 micrometer length scale, which is not too narrow. Actually, this 1 micrometer spin propagation distance or spin decay length is quite impressive for such kind of antiferromagnet. Particularly, the question to ask is, if either of both of the two magnon modes carry zero angular momentum, how can we understand that this antiferromagnet insulator can still participate in this kind of non-local charge transfer, which in principle can only be mediated by some finite spin current? So how can we reconcile this discrepancy? Well, now let's go back to look at those two eigenmodes. Okay, so now we see, okay, we have two eigenmodes, and those two eigenmodes are both linearly polarized. Each of them carries zero angular momentum. So if you have a conduction electron, excessive spins, they cannot, its spin cannot be carried by either of those two. However, actually, if we turn to the optics world, we may notice something similar. So that effect is known by birefringence effect. So we know in optics, if you have an anisotropic crystal, there are usually two principal axes. One is known as fast axis, and the other is slow axis. So that means the light for light polarized linearly along those two axes are the eigenmode of light inside the crystal. Then usually, if you have circular polarized light or you have a linear polarized light, you have to decompose first onto those two axes. And then after the light, well, those two linear polarized mode will propagate individually inside this crystal. After they exit this crystal, they will recombine together through a superposition, and then you will get the final output state of this transmitted light. So actually that's the underlying mechanism why people can make this kind of wave plate, like a quarter wave plate or half lambda wave plate. So basically that's how you can convert a linear polarized light into a circular polarized light or vice versa. Actually, we believe the same thing can happen inside this easy plane antiferromagnet. Again, you have linear polarized mode, but when you have a single incident electrons, when this conduction electron gets flipped due to its scattering with the magnons, actually it will lose each bar 1 unit of angular momentum. Then that means the generated excited magnons, the two magnons will be excited simultaneously because of the transfer of angular momentum. And their relative phase is fixed. So that means that's the reason why after you combine them together, you can get a circularly polarized spin. And then those two magnons will propagate individually inside this antiferromagnet. Of course, there will be velocity difference between those two magnon modes. And then finally, when you detect it, depending on the phase correlation between those two modes, you can get an elliptical polarized spin or elliptical polarized magnon or get a linearly polarized magnon, depending on their relative phase. So that means there is a finite coherence length for those two magnon modes. So we believe that this is the mechanism that accounts for our observation. How do we know that this is the case? Well, we can do some experiment to which can provide some evidence on this. The way that we do it is that we can change the temperature of this measurement. So we can either do a room temperature measurement or maybe do a low temperature measurement under 10 Kelvin. So the difference is that we will change the magnon distribution under different temperature. We know magnons satisfy the Bose-Einstein distribution. So basically at a very low temperature, only the low energy magnons get occupied. And for the low magnons, for the low energy magnon, you notice that those two modes are actually have very large difference in their velocity or very difference in their wave vector. So that means the coherence length is very short. And that's exactly what we found is that the propagation length is very short. And at a high temperature, you can imagine the high energy magnons will get excited. But for high energy magnons, they are nearly degenerate. So basically the energy difference is, the velocity difference is very small. So that's the reason why we observe a relatively larger spin decoherence length or spin decay length. So actually this behavior is consistent with the dispersion relationship of the two magnon modes inside the easy plane alpha R oxide. Okay, so finally, what can we do with this easy plane antiferromagnet? Because it's easy plane, so any in-plane orientation can be its equilibrium position. So we can do this experiment by applying field pulses in two orthogonal directions, H1 and H2. And after we apply H1, the new vector will be aligned along one direction. After we apply H2, the new vector will be aligned along the other direction. And we found that actually we can toggle the spin transmission coefficient between a high and a low states back and forth. So here we apply let's say a perpendicular field, a horizontal field, perpendicular field, horizontal field, and then we can toggle the spin current transmission from high, low states. So the on and off ratio is about 100%. So that's how we can modulate the spin transmission inside this antiferromagnet. Okay, so finally, let me summarize. In the first part, I showed that we can utilize the magnetic domain structure inside a ferromagnet to control the magnitude and phase of a spin wave. And in turn, we can also use a large enough spin wave current to induce domain motion or switch magnetic orientations. And in the second part, I talked about easy plane antiferromagnet. I showed that due to the superposition of two linearly polarized modes, we can realize a spin transmission in this easy plane antiferromagnet. And finally, I showed that we can toggle the near vector direction by using an external field to control the spin current transmission inside antiferromagnet. That's all. Thank you for your attention. Let me know if you have any questions.
Oh, thank you, Luqiao, for tell us about the two interesting tales of magnons, one in ferromagnetic material and the other one in antiferromagnetic material. Any questions from the audience?
Can I ask a question?
Sure, yeah, please.
I'm Walter Lambrecht. So I have two questions, actually. My first one was related to your nickel cobalt superlattice. If you go back to slide 10, maybe. Right, so I would, okay. Yes, here. So I was wondering why the hysteresis loop looks so strange for this system?
Well, I would say it's probably not too strange in our experiment. We saw these kind of features not too uncommon. The reason is, well, you see that there is a sharp switching close to zero. And then there are some long slope
Yeah, so where's it?
realized in the full switching. So usually this indicates it forms some multi-domain structure. So actually the domain gets expanded, nucleate, and they expand step by step. It gets pinned due to some local defect, and then finally finish the whole switching. So that's usually what we saw when the perpendicular entropy is not very strong. You will see this.
Okay, thank you. So which is related to my other question then. You know, domain walls can be thick or can be thin.
Yes.
Sometimes the spin flips over the shortest, and sometimes does that have any effect on, or were you able to, you know, distinguish these effects that you're talking about, the domain wall switching? You know, does that have a dependence on the thickness of the domain wall?
Yeah, that's an excellent question. So I definitely agree with you that there should be both of the two effects, basically the spin wave modulation and also the magnon-induced domain wall motion actually depend on details of this domain wall. But unfortunately, we were not able to modulate. We were not able to change the domain wall width inside our experiment. The reason is, as soon as you have this film, the domain wall width is determined by some energy consideration. So it's not so flexible. We do not have the knob to freely tune its width or its internal spin texture. But from simulation, actually, we do see some dependence. So depending on whether you have broad wall, blocker wall, or near wall, and also depending on the domain wall width, actually you do get different behaviors, or even in terms of the phase shift. But we are not able to experimentally verify that yet.
I see, but that's essentially a materials dependent problem. So if you have a different material, you could maybe see, or would it be something you want to optimize for? Would you like to have, you know, narrower domain walls or bigger domain walls to optimize this effect?
Yes. Ideally, you want to have some control over that, and then tune it, using it as turn knob. The reason is, for example, here, if you just want to control its magnitude instead of phase, then that's probably the most ideal for wave-based computing, because you do not want the other branch to have very weak intensity. So that's hopefully by changing the material property, we can optimize it. But so far, we haven't done anything along that line yet.
Okay, thank you.
Thank you.
All right, any other question?
So seems there are some ones.
I guess I have one.
I feel
it was very interesting when you switched from the ferromagnet to the antiferromagnet, but that the disadvantage of the perfect antiferromagnet was that you couldn't couple. So you had something that was almost an antiferromagnet. I guess that leads to the perhaps too obvious question. What about ferrimagnets? Do they have sort of disadvantages of both, or are there any possible advantages there?
Well, for ferromagnet, of course, it's in some sense it can be maybe combined advantage of both. So first of all, it can be easily controlled with external field, and secondly, there are also high frequency modes inside ferromagnet. Actually, if you want, you can also tune the ferromagnet into some almost antiferromagnetic state, in the sense that you can control the two sublattice so that they almost cancel each other. So that's something that we actually studied some time ago, but not in the concept, not in the framework of spin wave. The reason that we didn't use ferromagnet for, well, basically at least those high frequency modes for this kind of spin wave study is probably because, well, one thing is that it's not very easy to excite those kind of high frequency mode. Usually, if we excite a ferromagnet like yttrium garnet, which is a ferromagnet, but what we usually get is just its ferromagnetic mode. So we just treat it as a ferromagnet. It's not very common that we can excite the high frequency, the antiferromagnetic mode inside. But I think that's a direction. So there are existing efforts trying to tune ferromagnet into an antiferromagnet state so that it can behave more or less like antiferromagnet, but with additional advantages.
Thank you.
Thank you.
Okay, I see you. How you have a question?
Yeah. So at the intro part of the spin wave domain warp project, you talked about combining the two spin waves to do spin wave computation, that kind of thing. Have you tried testing this? Yeah.
No, this is only still a schematic. This is just conceptual drawing. So this is, you can imagine, in terms of engineering, this requires some sophisticated fabrication method, control method in order to really realize this. So we haven't got to that step yet. No, we don't.
I see. Have you tried simulation?
Simulation we didn't try, but there are simulation. I think there are more than one simulation works where people study it from theoretical or analytical or numerical approaches. Yes.
Thanks.
Thank you.
All right. Any other questions from the audience? Okay, I ask the last question then. So for the antiferromagnetic magnons in the system, you mean you mentioned that the net moment is induced by the Dialogin-Scheme-Maria interaction, which only present when the material has a broken inversion symmetry.
Yes.
And usually in those materials with broken inversion symmetry, one would expect to have some non-reciprocal response. Do you see anything like that, any signature?
That's a good question. So no, actually, we do not see this non-reciprocity inside this. Sorry. Where is it? Yeah, we did not see any non-reciprocity in this experiment.
Mm-hmm.
So I guess the DMI probably doesn't work in the correct direction. For example, previously when people utilize DMI to realize non-reciprocal transmission of spin wave, what they usually do is that they study it in the mode where the spins actually is perpendicular to the transmission direction. So that's where you get the non-reciprocal transmission due to DMI. But in this case, actually the transmission, our largest transmission happens when the spins in the neo vector is parallel with the propagation direction. That's how you can excite those neo vectors. So no, we didn't. This configuration is probably hard to use non-reciprocity. This is obvious. Thank you. That's a very good point.
Thanks. If there's no further questions, then let's thank our speaker again.
Thank you. Thank you.
We'll stop the recording and have unrecorded informal session if you have further questions. Okay, let me stop the recording.